Well, it's China versus the United States in the battle for AI dominance, and China is closing the gap. In fact, when it comes to usage and cost, China is now in the lead.
NVIDIA is denying a report that it plans to begin shipping a new AI chip designed for Chinese customers.
China just announced something the semiconductor world had largely written off as impossible under current conditions. Not in this decade. Not without access to the most advanced chip-making tools. And certainly not by a company that has been blocked for years from buying those tools. Yet the claim is now public. Huawei, the Chinese technology company that US restrictions effectively cut out of the leading-edge global chip supply chain, has described a new way to improve processor performance. If the numbers hold up, the approach aims to reach density and performance levels that people normally associate with much more advanced process nodes without using the extreme ultraviolet lithography machines that make those nodes possible. No ASML EUV tools. No access to the equipment the rest of the industry treats as essential. The claim sounds extreme. In some ways, it is. But the idea behind it is not about making individual transistors dramatically smaller. It is about rearranging how the chip is laid out so that information travels shorter distances. Once you understand that shift, you can see why engineers around the world are watching closely. This video will walk through the announcement in plain language. No heavy jargon. No confusing diagrams. Just the actual story of what Huawei presented, why it matters, and what would have to go right for the approach to succeed at scale. If you find this kind of breakdown useful, hitting the like button genuinely helps. These videos require a lot of research. And if you want to stay ahead on stories like this, subscribe and turn on notifications so you do not miss the next one. For roughly 60 years, the technology industry ran on a single powerful idea. Make the parts smaller and everything else improves. Smaller transistors mean more of them, fit on a chip. More transistors mean more computing power. More power means better phones, computers, and almost every other digital device. That pattern became known as Moore's Law. It worked so reliably for so long that most people assumed it would continue indefinitely. Every couple of years, engineers found a way to shrink transistors again, pack roughly twice as many onto the same area, and deliver a jump in performance while costs per transistor fell. The streak is one of the most impressive in the history of engineering. We moved from thousands of transistors on a chip in the 1970s to billions by the 2000s and to hundreds of billions today. The processor inside a modern smartphone has more computing capacity than the room-sized supercomputers of a few decades ago. The gains are no longer coming as easily. The improvements that used to arrive every 2 years now often take longer. The cost of staying on the leading edge has become enormous. Building a new advanced chip factory can cost around $20 billion. Developing a single new generation of transistor technology can cost $1 billion before the first commercial chip is made. Even the leading foundries are now talking about single-digit percentage improvements in area efficiency from one generation to the next. The easy progress is largely gone. The remaining progress is expensive and difficult. For Huawei, the problem is more specific than general industry slowdown. Beginning in 2019 and tightening in the years that followed, US export controls restricted what technology could be sold to the company. By the early 2020s, Huawei and the Chinese foundry that manufactures many of its chips were effectively cut off from the most advanced lithography equipment in the world. The critical machine is the extreme ultraviolet, or EU, lithography system built by the Dutch company ASML. These tools use a complex process involving tin droplets and extreme ultraviolet light to print the tiniest circuit patterns onto silicon. Each machine costs hundreds of millions of dollars, weighs as much as a commercial airliner, and is essential for the most advanced process nodes used by companies such as TSMC and Samsung. Huawei cannot buy them. The Chinese foundry that works with Huawei cannot buy them either. When a company is blocked from the tools that define the leading edge, it has two broad options: accept a permanent gap or find another way to improve performance. Chinese engineers have already pushed older deep ultraviolet or DUV lithography systems further than many outsiders expected by using multiple patterning, printing a complex pattern in several simpler steps. Instead of one day of produced chips at what is roughly considered a 7nm class level, that is a genuine engineering achievement. Every extra patterning step, however, adds cost, complexity, and opportunities for defects. There is a practical ceiling on how far the approach can be stretched. Huawei's engineers, therefore, began asking a different question. What if making transistors smaller is not the only way to make chips better? Here's a fact that surprises many people outside the industry. Modern computers are often limited less by how fast individual transistors can switch and more by how long it takes information to travel from one part of the chip to another. In some systems, more than 80% of the energy can be spent simply moving data around rather than performing actual calculations. The computing elements themselves are not the main bottleneck. The wires that connect them are. Picture a chip as an extremely dense city packed into an area smaller than a fingernail. The transistors are the workers. They are connected by a network of metal wires that run across more than 20 layers. Every time a signal travels along those wires, it encounters resistance. And the wires themselves act a bit like tiny capacitors that must charge and discharge. Engineers call the combined effect RC delay. The longer the wire, the worse the delay, and the higher the energy cost. This is one of the main reasons clock speeds in mainstream processors have risen only slowly for about 15 years. The transistors can switch faster. The signals cannot always keep up across long distances. If distance is the problem, one possible solution is to make the distances shorter not by shrinking every transistor further, but by rearranging where the transistors sit relative to one another. Instead of spreading everything out in a single flat layer, what if parts of the logic were stacked on top of each other like floors in a building? Signals that once had to travel millimeters across a flat plane might only need to travel a few micrometers vertically. Huawei's approach, presented under the name Tau scaling and implemented through a design method called Logiv, is built on exactly that idea. The basic concept is easy to visualize. Take a sheet of paper covered with text. Words at opposite corners are far apart. Fold the paper in half, and those same words are now separated only by the thickness of the paper. Huawei wants to do something similar with a processor. Divide the logic, place one portion above the other, and connect them with a dense array of vertical bonds. Pads that used to span millimeters shrink dramatically. When the journey shortens, the delay, the energy, and the heat generated by moving data all improve. In early results associated with the Kirin 2026 generation, Huawei has reported transistor density rising from roughly 1 million transistors per square millimeter to about 238 million, an increase of more than 50%, while staying on the same process node that was available without EUV. The company has also claimed power reductions on the order of 40% at equivalent performance, along with improvements in clock frequency. Looking further ahead, the roadmap presented in 2026 suggests that continued refinement of the stacking approach could deliver density and performance levels that the industry currently associates with a 1.4 nanometer class process by around 20, still without access to EUV tools. It is important to be precise about what those nanometer labels actually mean. In modern chip marketing, the nanometer number is more of a performance and density shorthand than a literal physical measurement of transistor size. Huawei is not claiming to have invented a new transistor that is literally 1.4 nanometers wide. The claim is that by stacking layers of an existing process, they can pack enough transistors into a given footprint and reduce interconnect delays enough to compete with what a more advanced single-layer process would deliver. That is still a significant engineering statement, but it is a system-level and packaging-level achievement rather than a pure transistor scaling breakthrough. One number in particular has drawn close attention from semiconductor engineers: the bonding pitch. When two chip layers are stacked, they must communicate through a dense array of tiny copper connections that bond directly from one layer to the other. The spacing between those connections is the bonding pitch. The smaller the pitch, the more connections can fit in a given area, and the faster data can move between layers. Today's leading commercial 3D stacking technologies operate at pitches measured in several microns off-on, in the range of 9 microns or higher for certain high-volume applications. Huawei has described a target of 1.5 microns for its hybrid bonding process, with further reduction planned. Achieving a pitch 6 times tighter than many existing solutions is not a modest incremental step. It requires advances in equipment, materials, alignment, accuracy, and testing. If the company can manufacture it at high yield, the two stacked layers begin to behave, from a performance standpoint, more like a single dense processor than like two separate chips glued together. Then physics intervenes. Memory chips that mainly store data generate relatively little heat. Logic chips that switch billions of times per second generate a great deal of heat. In a conventional flat package, that heat can escape upward and downward into a heat spreader and then into a cooling system. In a phone, the cooling system is limited thin metal, graphite sheets, and the requirement that the device remain comfortable in a human hand. When one hot logic layer sits directly on top of another, the heat from the lower layer has a harder path out. The stack becomes a thermal sandwich. Managing that heat is one of the hardest practical problems in the approach. Research groups are exploring better thermal interface materials and even microscopic channels that carry cooling fluid through the silicon. But none of those solutions is yet proven at the volume and cost required for a mainstream smartphone chip. Whether Huawei has a credible, manufacturable answer to the thermal challenge will largely determine how far logic folding can go in mobile devices, even if every technical piece works. The economics are different from classic Moore's law. Traditional scaling improved both performance and cost per transistor at the same time. Stacking adds process steps, more precise alignment, and additional testing. The resulting chip can deliver more capability in the same footprint, but it is not automatically cheaper. The industry is trading higher manufacturing complexity for higher density and shorter In a world where traditional geometric scaling has slowed, that trade-off can still be valuable. It is simply a different kind of progress. Huawei is not the only company thinking in 3 dimensions. AMD already stacks memory on logic. High bandwidth, memory stacks, multiple memory Intel and TSMC both have advanced packaging roadmaps that include hybrid bonding and 3D integration. Research laboratories are exploring transistors that are themselves stacked vertically at the atomic scale. The direction of travel for the industry was already 3-dimensional. What Huawei is doing is pushing the idea harder and faster. Partly because the company has no access to EUV, and partly because it has the engineering resources to attempt an aggressive implementation. The 1-0.5-micron bonding pitch, if achieved in volume, would be a notable milestone. The density numbers reported from early implementations appear consistent with the architectural claims. They are not the same thing as possessing a true 1.4 nanometer manufacturing process, but they represent a real alternative path. The full realization of the roadmap is projected around 2031. 5 years is a long time in semiconductors. Many details can change. In the near term, the questions to watch are whether the Chinese foundry partner can manufacture the bonded stacks at acceptable yield, the percentage of chips that actually work, and whether the thermal solutions for a stacked Kirin processor in a phone prove practical. Yield is often the hardest part of advanced manufacturing. A design that works in the laboratory but fails half the time on the production line is not yet a product. As more technical details emerge about heat management in the stacked logic, the industry will have a clearer signal of how production-ready the approach really is. If the bonding technology and the thermal solutions both succeed, other companies will accelerate their own 3-dimensional packaging programs. The competitive race will not end. It will simply shift into a new arena where interconnect density and heat extraction matter as much as pure transistor size. That pattern has repeated throughout the history of semiconductors. Every time someone declares a particular path closed, someone else finds a different route. The route is not always the one the skeptics imagined, and it is not always delivered on the original schedule, but progress continues. Huawei's announcement is not proof that the company has already closed the gap with the most advanced process nodes. It is proof that the company is still actively searching for ways to improve performance under severe equipment constraints. In a field this important, remaining a serious participant is itself significant. The next few years of manufacturing results yield data, and real smartphone performance will show how far the folded chip approach can actually go. That is the story of what Huawei presented and why the semiconductor world is paying attention. If you stayed with the explanation to the end, A-Like helps the channel reach more people who want to understand how these technologies actually work. Subscribe and turn on notifications so you catch the next deep dive. And I want to know what you think. Do you believe the heat problem in stacked logic can be solved well enough for a real high-volume smartphone chip, or will thermal limits keep the approach from reaching its full roadmap potential? Leave your view in the comments.